All right, so let's work through a couple thrilling problems to help us better understand Hess's law and how it works as a state function. First, we're asked to find the enthalpy change for the formation of lead-4 chloride by the reaction of lead-2 chloride with chlorine provided to us here. I wonder what the enthalpy change could be. We're given several thermochemical equations with known enthalpy changes for those equations and asked to determine what the enthalpy change is for this unknown. Well, using Hess's law, we can keep this first reaction the same, PbS, solid, plus 2 moles of chlorine gas will form 1 mole of liquid lead-4 chloride. And because I did not manipulate this equation in any way, my enthalpy change will remain unchanged. Now, as I look at my second equation, I'm going to invert that or reverse that equation to give me the lead-2 chloride as a reactant, forming the solid lead and chlorine gas as my products. And the reason why I want to do that is I'm trying to determine the enthalpy change for this reaction overall. And I notice that I've got the lead-4 chloride as a product, which is given to me in this first reaction, but I need both lead-2 chloride and chlorine gas as a reactant. Well, that first equation will give me the chlorine gas as a reactant, but I need to reverse the second equation to give me the lead-2 chloride on the reactant side of that equation. So because I reversed the equation, my enthalpy change will become positive 359.4 kilojoules. Now, all we have to do, Hess's law here indicates we can sum together the reactions and therefore sum together our enthalpy changes. Now, keep in mind sort of how Hess's law works. Anything that appears on the reactant side that's also on the product side of a separate equation will sort of cancel out of your overall reaction. So the solid lead will cancel out, and the chlorine on the product side will also cancel out, and I'll be left with 1 mole of chlorine gas on the reactant side. And so ultimately, I'm left with overall on the reactant side, PbCl2 in the solid state plus 1 mole of chlorine gas to form 1 mole of lead-4 chloride in the liquid state, which is the reaction that I'm looking for. Again, note that anything on the reactant side will cancel out anything on the product side in a second equation. Our enthalpy changes can then be summed together to determine the overall enthalpy change of the combined reaction. And for this reaction, we would determine that enthalpy change to be positive 30.2 kilojoules. Boom. All right, moving right along here. Question number 2 is another example of Hess's law, which is a little trickier than the first one. But again, same idea. Again, Hess's law is going to allow us to sum together the individual enthalpies of individual reactions to get the overall enthalpy change of a desired reaction that we're looking for. In this case, we are asked to find the enthalpy change for the formation of pentane C5H12. Wow, great organic nomenclature practice right here. By the reaction of carbon with hydrogen. Use the following thermochemical equations. We're provided with their enthalpy changes. Okay, again, we're trying to get this equation from these equations here. So we want carbon and hydrogen as reactants and pentane as a product. As I look at the first reaction, the only part of this that is part of the desired reaction is carbon. And I see that it is on the reactant side, so I'm just going to leave this reaction as is, where carbon still stays on the reactant side. Whoop. Now, because I haven't changed anything about this equation, I'm going to keep my enthalpy change unchanged as well. As I look at the second equation, again, I note that hydrogen is the only thing that is in this second equation that matches what I want in the desired equation. It's also already on the reactant side, so I'm going to maintain that reaction sort of unchanged. Now, as we work through Hess's law problems and the rest of this thermochemistry and thermodynamic unit, you'll start to notice these fractional coefficients. And many times that's because we're working with heats of formation, where again, it's going to be the formation of 1 mole of a compound from its elements in the standard state. And so sometimes that means because our goal is to form 1 mole of a compound, you'll see these fractional coefficients for the elements in their standard state. Not a big deal, not something to freak out about. Just recognize that you may start seeing these fractional coefficients as you work through these thermochemistry problems. Okay, as we look at the third equation here, I notice we've got pentane in our equation, but it's on the reactant side. However, in the desired equation, we've got it on the product side. So we're going to reverse that equation, which will give us carbon dioxide and water as reactants. And the formation then of our pentane as a product, and oxygen gas. Now, because I have inverted my equation here, or reversed my equation, I'm going to change the sign of my enthalpy change from negative to positive. And again, as I look to derive this desired equation from the ones that are provided, I recognize that I'm going to need to cancel out some of this oxygen. I'm also going to need to cancel out this carbon dioxide and cancel out some of this water, because all I want is this 5 carbons, 6 hydrogens to form 1 mole of the pentane here. So as I think about how I'll be able to achieve that, I think a good idea would be to probably multiply this reaction by 5. So I get my 5 moles of carbon here. I'm feeling pretty good about that. As I look at the second equation, I need 6 moles of hydrogen, so I'm going to multiply this whole thing by 6. If I multiply 6 by 1/2, that'll give me 3 moles of oxygen, and you'll see how conveniently that works out for us. But as I look then, I'm going to leave the third reaction, other than reversing it, unchanged. As I sum these equations together, essentially completing Hess's law here, you should recognize that the 5 moles of oxygen on the reactant side in the first equation plus the 3 moles of oxygen on the reactant side in that second equation will effectively cancel out the 8 moles of oxygen on the product side of that last equation. Additionally, my 5 moles of carbon dioxide in the product side of that first equation will cancel out the 5 moles of carbon dioxide on the reactant side in that last equation. Likewise, adios, those 6 moles of water, which will leave me then conveniently with 5 moles of solid carbon plus 6 moles of hydrogen gas, forming our 1 mole of pentane in the gaseous state. As I determine my enthalpy change, though, you need to keep in mind that because you multiplied the first reaction by a coefficient of 5, you also have to multiply this enthalpy change by a factor of 5. Essentially, you're going to get 5 times the release of heat in that first reaction, as well as 6 times the release of heat in the second reaction. Now, we're not multiplying the third reaction by any coefficient because we didn't multiply our equation by any coefficients, although do keep in mind we did change the sign because we reversed that last equation. When you bust out your handy-dandy calculatora and add all of these together, you should get an enthalpy change of this last reaction to be negative 146.7 kilojoules per mole, which is our enthalpy change for the formation of pentane from its elements. Boom.